for the final day of the workshop. The first speaker is Dr. Jayatra Chattopadhyay. He did PhD in HRI. After that, he was a postdoc at IIT Guwahati. Then he got, right now he is currently assistant professor in Vishwa Bharati. Jayatra, please. He is going to talk about Polya groups of consecutive number fields. Everything he has to explain, okay?
Shall I start? Yeah, I think I am audible to everyone. Yeah, thank you, sir, for the warm introduction, and I would like to thank Adhikari, sir, for inviting me here. So, last time I was here delivering a talk was in 2019, when there has been a workshop cum conference. So, it's good to be back here again. Yeah, so as the title of my talk suggests, that it will be some sort of an overview on the topic of Polya groups of something called consecutive number fields. So I will try to make it accessible to everyone and try to make it make the exposition in such a way that most of you are able to understand most of it. So yeah. So before going into the definition of Polya groups, let me first give you the motivation behind why we are interested in considering this question. So this background essentially comes from something called integer valued polynomials. So we all know what a polynomial is. It is just an expression in some indeterminate x, something like a0 plus a1x plus a2x square up to some finitely many terms. So now it's a trivial observation that if we consider some polynomial with integer coefficients, so the coefficients are allowed to come from the ring Z, then if we put any integral value in place of x, then the resulting number is an integer, because the coefficients are all integers. So if we put x from Z, then the resulting thing will be an integer. But if we allow the coefficients to be rational, then sometimes it might also happen that the integral values of x will give the resulting number to be an integer. For example, if we first consider the polynomial x into x minus 1 over 2, then this polynomial has certainly coefficient in q but not in z. But if x is an integer, then it is x into x minus 1, means the product of two consecutive integers, and therefore exactly one of them is even and the other one is odd. So when we divide it by 2, so the even number will be cancelled out by 2, so the resulting rational number will be an integer. So x into x minus 1 by 2, even if it has coefficients in the field q, but for integral values of x, the resulting value is in z. Similarly, if we take a prime number p, then x to the power p minus x over p, this polynomial also has coefficient in q, but by virtue of Fermat's Little theorem, always we know that if x and p are co-prime, then x to the power p minus 1 is congruent to 1 mod x, and if p divides x, then anyway x to the power p minus x is divisible by p. So for all integral values of x, x to the power p minus x upon p, this is also an integer. So we see that even if for some cases, if we allow the coefficients to come from q, the resulting value is in z. That's why we define the quantity called int of z, that is the collection of all polynomials with rational coefficient that takes integers to integers. And we, from these two examples, we can see that this set is indeed non-empty. Now, the next thing that we can hope for is a good characterization of this set, like what are the, right, of course. And the next question is, how can we characterize this set? Means, what is the minimal set of elements we need to know so that we can generate every other element. So this theorem by Nagel and Polya, this dates back to almost 100 years ago. So what they proved is that any polynomial with rational coefficients that is actually coming from the set int z, if and only if, that's an integer linear combination of these kind of polynomials hix. So what is HIX? It is just the product of I many polynomials divided by I factorial. So we know that the product of any consecutive n integers is divisible by n factorial. So likewise, x into x minus 1 by 2 is integer valued. Similarly, x into x minus 1 into x minus 2 by 3 factorial, that is also integer valued. So x into x minus 1 into x minus I plus 1 over I factorial, that is also integer valued. So this HIX, all these polynomials are all integer valued. So their theorem tells us that any polynomial in int z can be uniquely expressed in this way. So now we take this concept a little bit further and ask the same thing for a number field. So what is a number field? A number field is a finite extension of the field Q. So for example, Q root 2, Q adjoint cube root 2, like this. So given a number field K, we can consider the ring of integers which is denoted by OK. So the ring of integers is nothing but the integral closure of Z inside K. Means we take all the polynomials that are with integer coefficients and monic and take the roots of those polynomials. Those are algebraic integers inside K. So we have a number field K with the ring of integers OK, and with that comes the this group called the ideal class group, which is defined by the quotient of fractional ideals by the principal fractional ideal. So essentially, class group is a measure of extent of failure of the number field or the ring of integers rather from becoming a PID. So the class group is trivial if and only if the ring of integers is a principal ideal domain. For example, the number field Q, Q root 2, these are all having class number 1 and their ring of integers Z, Z root 2, etc. They are all PID. And it is known that for any number field K, the class group is a finite abelian group. So the order is what we call the class number of K. Now for any number field, we can also define the way we had defined int of Z, this set called int of OK. This is the collection of all polynomials with coefficients from K that takes the ring of integers to itself. Likewise, for K equal to Q, OK was Z. So int of OK in case of K equal to Q is nothing but int of Z. So now this int OK, this set, we can endow it with an OK module structure. So to give some set, some module structure, what we need to do is to define some function from OK cross int OK to int OK. So some element we are taking alpha from OK and taking some polynomial f, we are sending it to alpha times f. So we can check that this is indeed giving it an OK module structure. Now the algebraic question we can ask is whether this module has some nice structural, some structure in terms of a basis called regular basis. So a collection fi of polynomials in int OK, we call that to be a regular basis if any polynomial in int OK can be expressed uniquely as an integer linear combination of this f1, f2 like this set. Now the point is this definition is actually motivated from the theorem of Polya and Nagel. Yes. 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 So we are allowing these AIs to come from integers. Yes. Yes, we are allowed to vary these integers AI. So we can, play around with that. So now this definition is essentially coming from this theorem of Polya and Nagel as a motivation. And we call a number field to be a Polya field if this module int OK has a regular basis. No. Now this characterization in terms of this module structure, it is seemingly impractical in the sense that if I give you a number field K and ask you to check whether int OK has a regular basis, it is not always easy to check or to come up with some regular basis of int OK. So naturally we are led to find some practical criteria as to how to check whether some field is Polya field or not. So that's where the arithmetic of number field comes into the picture. Arithmetic of number field means if some property can be captured or expressed in terms of the ideal class group of K. So for that we introduce another definition called the Polya group of K. So what is a Polya group? Given a number field K, we have the ideal class group CLK, and inside that we take the subgroup generated by the classes of all these ideals of same norm and take the product. So we know that the norm of a prime ideal is a prime power. So if some integer is a prime power, then there will be finitely many prime ideals with that norm. We take the product of all those prime ideals. The resulting product will also be an ideal. We take the ideal class of that product and we collect all those ideal classes and generate the subgroup inside the ideal class group. Since the ideal class group is finite, this will also be finite. But the point is, this may not be equal to entire group CLK. So whatever group we generate in this way, that is called the Polya group of K. So that's how we define the Polya group of a number field K. No, actually, if Q is a prime power, then we have finitely many prime ideals of that norm. We take all those, yes, and take the product. Now, if we change another Q, then there will be some other prime ideals of that norm. We take the product and then we have a different element. Now we are generating a subgroup inside that ideal class group. Now, if Q is not a prime power, then certainly there is no prime ideal of that norm. So in that case, we define it to be the entire ring OK. Now, when we take the ideal class of OK, that is nothing but the trivial element inside the ideal class group. So that is not contributing anything non-trivial to that group. Now, notice that the definition of Polya group, it has nothing to do with the integer valued polynomial thing. Now, a celebrated theorem due to Polya is that, obviously he didn't coin this term Polya field, it was introduced much later. He says that K is a Polya field if and only if this group POK, that is trivial. Means if we are given a number field K, all we need to do is to check whether this subgroup of CLK POK, that is trivial or not. If that is trivial, then we are ensured that the OK module int OK, that has a regular basis. So clearly it follows, since POK is a subgroup of CLK, if the superset means CLK is trivial, then obviously POK is trivial. So any class number 1 number field is automatically a Polya field. So we have some examples of non-trivial Polya fields. For example, Q root 2, we know that its class number is 1, therefore it is a Polya field. Now notice that this does not give us any algorithm to find an integral basis. This is kind of an existential result. Then the question is, what if Hk is not equal to 1? So if Hk is not equal to 1, it doesn't trivially follow that the Polya group is trivial. Yes. No, they didn't provide a basis. Actually, they introduced something called characteristic ideals. So the way we prove that if some ring is Noetherian implies the polynomial ring is Noetherian, the proof goes something like this. We take some ideal, so that consists of some polynomials, and we take the the leading terms and generate the ideals and use the Noetherianness of that ring. Something similar approach is taken there. Yeah. So now the question is, what if Hk is not equal to 1? Means if the class number is bigger than 1, then can it happen that POK is still trivial? That may happen, that may not happen. Now the answer is affirmative. It is known that every cyclotomic field is a Polya field. So there are infinitely many cyclotomic fields Q zeta n. We can keep on varying our n. And it is also well known that only finitely many of these cyclotomic fields, they have class number 1. So apart from all those cyclotomic fields of class number 1, all the remaining things, they do not have class number 1, but still their Polya group is trivial. So we do have examples of number fields with non-trivial ideal class group, but trivial Polya groups. Then this brings us to the next level, that what are the number fields that are Polya but of small degree, means degree 2, 3, 4, 5, etc. like this. So in 1982, Zantema classified the class of all quadratic Polya fields in this way. So he proved that some Q root D is a Polya field if this falls into only these 5 categories. So D, you look at the prime factorization of the discriminant D, and the surprising thing to note here is that D is allowed to have only at most 2 prime factors. In none of these characterizations, D has more than 3 factors. Yes, right, because of Gauss theory. Because Gauss theory tells us that if a quadratic field has more than n prime factors, if it is real, then 2 to the power n minus 2 will divide the class number. So we cannot allow that thing here. Yeah, so then comes the classification of cubic Polya fields. It came much later in 2013, and it has been done only for the case of cyclic cubic fields. And Ledishe proved in 2013 that some cyclic cubic field whose defining yeah, that is also here. No, D equal to -1, -2 and D equal to -p. Yes, yes. Because obviously we know that there are only finitely many imaginary number fields of class number 1. So if P is sufficiently large, then D, the 5th point tells us that D equal to -p will always have POK trivial. But class number still bigger than some, I mean at least bigger than 1. Now the classification of cubic Polya field is given in this way, that we look at the defining cubic polynomial, and if the defining cubic polynomial satisfies these two conditions, these two stringent conditions rather, then the cubic field is Polya field. And then the classification of biquadratic Polya field comes. This has some restriction, that it assumes that the biquadratic field q square root m adjoint square root n, this is Polya under the assumption that individually the quadratic fields q square root m and q square root n are Polya. Then what are the prime factorizations of m and n? In those terms only the classification has been made. So now this gives us that all the results that we have discussed so far, that tells us about the Polya fields of quadratic, cubic and biquadratic nature. Now what are the fields that are not Polya, means POK is not trivial? Can it go arbitrarily large or does it have some bound? So from some work of Hilbert, it follows that if we take a quadratic field q square root d, then the order of the Polya group is nothing but 2 to the power the number of ramified primes minus some factor. If it is real quadratic field and the fundamental unit has norm 1, then it is 2 to the power number of ramified primes minus 2, and otherwise it is -1. So this actually tells us that if a quadratic field q square root d has too many ramified primes, then its Polya group will be much larger. So if d has suppose 10 prime factors, then it will have some 2 to the power 8 or 2 to the power 9 Polya groups, then order of the Polya group. Now Polya group of biquadratic fields, there are some known cases like q square root p and square root qr. If this kind of biquadratic fields we take and we allow certain Legendre symbol conditions among them, then these are the results that are known, that in some cases the Polya group is trivial, and in some other cases the Polya group is isomorphic to Z mod 2Z. So now the question is, what are the remaining cases? Whatever has not yet been covered in the previous theorem, can we say something about the Polya group of those fields? So this is a recent work that I did with Professor Anupam Saikia while I was a postdoc there at IIT Guwahati. So this says that if we take a biquadratic field of this form q square root p and square root qr, and in the last one q square root 2 adjoins square root pq, where p and q are distinct odd primes coming from certain arithmetic progressions given by either 3 mod 4 or 1 mod 4 depending on the situation, and there are some mild Legendre symbol conditions among those primes, then in these three cases the Polya groups are all isomorphic to Z mod 2Z. Since it is isomorphic to Z mod 2Z, it is not trivial, and therefore these fields are not Polya. And this also tells us that since POK is a subgroup of CLK, so 2 divides the class number of these, because in a finite group the order of a subgroup divides order of a group. So it's just a simple restatement of Lagrange's theorem in this setup. Yes, yes. If it is cubic, then it will be a power of 3. Yes. If it is cyclic cubic, I should be precise. We don't know much about the nature of non-Galois fields, because the key ingredients in all these proofs is the result of Xan lemma that assumes certain thing about the Galois extension k over q. That's why the primary assumption should be that k over q should be finite and Galois. Now we come to the topic of this talk, that is the consecutive Polya field. So first of all, what is a consecutive field? So if we consider quadratic field, the description of a quadratic field is quite apparent. It is given by q square root d, where d is a square free integer. Now we call two quadratic fields to be consecutive if they look like q square root d and square root d plus 1. So notice that while defining the notion of consecutiveness, we do not require both d and d plus 1 to be square free, because that would be too much to ask. Because if we then want to ask for 10 consecutive fields, that means d plus 1 up to d plus 9, all this has to be square free, but that is not the case, because something or the other will be divisible by 4. So we call two quadratic fields to be consecutive if they are of this form q square root d plus 1. Now this whole business of consecutive quadratic fields and the study of their class numbers got inspired from a paper by Iizuka in 2018, where he proved that there are infinitely many pairs of consecutive imaginary quadratic fields, means imaginary quadratic fields of the form q square root d and square root d plus 1, such that the class numbers of all of them are divisible by 3. And he made a conjecture that this phenomena has nothing special about the prime 3. If we take any integer k, then q square root d plus 1 up to d plus k, such type of infinite pairs will exist. Infinitely many pairs will exist, all of whose class numbers are divisible by any given prime L. This is the precise nature of the conjecture, that for any given prime number L, which is bigger than or equal to 3, and given any integer k, which is bigger than or equal to 1, there exist infinitely many k tuples of the form q square root d plus 1 to d plus k, such that all of their class numbers are divisible by L. Now, what about large class numbers? So we know that some class number is divisible by 3. It may happen the class number are all equal to 9 or 27 or say equal to 3. Then we cannot make it as large as we want. Now this result of Ankeny and Chawla proved in 1955. They proved, actually this result was also known prior to this in 1922 by Nagel, but many people would like to refer to their result because this actually gives a quantitative version. They proved that for any given integer g, there exist infinitely many imaginary quadratic fields with class number divisible by g. And the later this real counterpart, it was also proved sometime 20 years later in 1973 by Weinberger. So now, combining these two theorems, we can say that there are infinitely many quadratic fields, both real and imaginary, with large class numbers, because we are allowed to take integers g with our choice. So if we take g to be 10 million, then there will be infinitely many imaginary quadratic fields with class number divisible by 10 million. That means at least 10 million. Now the question comes, among those infinitely many number fields, can we find consecutive pairs or triples or quadruples like this? Then in 1928, actually Littlewood proved some interesting result. He proved that the number of real quadratic fields with class number divisible by something, or class number is larger than some portion, is at least some constant times square root d times log d upon log d, and this bound is sharp. So whenever we say that some bound is sharp, means that the exception will be there up to some constant for infinitely many such fields. Now the question is, if there are infinitely many number fields whose class numbers has an upper bound, has a lower bound of square root d log d by log d, in those infinitely many pairs, can we find consecutive number fields? This makes the question non-trivial, because already we know that for density 0 number fields, there are such exceptions and that set is infinite. Now we are asking for more, whether among those thin sets does there exist some consecutive pair or triples. So very recently in 2023, a group of mathematicians proved that for any fixed integer k, there exists at least x to the power half minus little o of one many integers d which are less than equal to x, such that the class numbers of all these quadratic fields q square root d plus 1, d plus 2 up to d plus k, these are all bigger than square root d log d upon log d. So little o of 1 means some quantity that goes to 0 as x goes to infinity. Now this is a quantitative result. So the weaker question we can ask is, whether given any integer m, does there exist some k tuples of quadratic fields, all of whose class numbers are bigger than m? So this is a joint result with Professor Saikia. So we proved that for any given integer k and some positive real number m, however large, there exist actually k consecutive real quadratic fields of this form, all of whose class numbers are bigger than m. And the proof actually is not so difficult. So let me just give you an outline. So for a given m, we choose an integer n such that 2 to the power n is bigger than m. We want to ensure that the d plus 1 up to d plus k that we want to cook up will have at least n plus 2 distinct prime factors appearing to an exponent of 1, because whenever we take a square root, those primes we want to keep there. So for that we choose some pairwise disjoint sets of prime numbers, each consisting of n plus 2 primes, p1, 1 up to p1, n plus 2, then p2, 1 up to 2, n plus 2, likewise pk, 1 up to k, n plus 2. So these are the primes we choose, all are bigger than k, and we form this system of congruence x congruent to minus I plus p of I, j mod pij of square. Since all these primes are distinct, so the modulus are all distinct. So we can apply Chinese remainder theorem to catch hold of some integer d which is unique modulo the product of the moduli. Now what is the feature of this integer d? That d satisfies all these individual congruences. Means d plus I is divisible by pij but not divisible by pij square. That means whenever we take the square root of d plus I, pij will remain. So at least n plus 2 prime factors are appearing there with exponent 1. So all these quadratic fields q square root d plus I will have n plus 2 odd prime factors appearing in exponent 1. So all of them will contribute something to the order of the Polya group, and it will be at least 2 to the power n, which is assumed to be bigger than m. So all of their Polya numbers are bigger than m. And we have to ensure that these fields are all distinct. So there is a common technique to show that some family of quadratic fields consists of distinct fields by using the theory of ramification. So if we want to show that q square root d plus I and q square root d plus I prime, they are distinct, all we need to show is that there is some prime number which is ramified in one quadratic field but not ramifying in other, and vice versa. So if we look at d plus I prime for some index I prime different from I, then we can see that d plus I prime is not congruent to 0 mod Pij, because otherwise it implies that I is congruent to I prime mod Pij, which is clearly false because they are all within the range of 0 to k. And if some integer bigger than some integer has to divide it, that means the only choice it has got is to be equal to 0. So Pij is ramified in q square root d plus I, but stays unramified in the other field, and Pi prime j, that is unramified, that is ramified in the second one but not in the first one. Therefore these fields are all distinct, because had it been same, then the number of ramified primes in both the sets would have been same. So therefore these are all distinct fields. And a remark says that in this way we can actually try to generate infinitely many such k tuples. So the technique of the proof shows us that given any k and m, there exist some k tuples of quadratic fields, all of whose class numbers are bigger than m. Now the question is whether there exists only one k tuple or infinitely many k tuples. So that is actually easy to see. How do you do that? So by the previous theorem, we know that one such k tuple exists. So let's call it q square root d plus 1 up to q square root d plus k. All of these fields has some class numbers. So yes. Yes. No, but those solutions are unique modulo the product. No, so I think those ramification argument will not go through them. But yeah, actually more elementary argument will settle the problem. Like we take this set of number fields and look at their class numbers. So that's a finite set of integers. Let h be the maximum of those numbers. Now we repeat the argument for h in place of m. So then there will be again some q square root d prime plus 1 up to q square root d prime plus k, all of whose class numbers are bigger than h. Okay. Now we have to ensure that this family q square root d prime plus 1 to q square root d prime plus k, these are distinct from the previous family. Now why is it distinct? Because the class numbers of these families are all bigger than h, while the class numbers of all those, the former ones, are all smaller than or equal to h. Therefore the class numbers do not match, therefore the fields have to be distinct. Okay. Now again we can repeat this to obtain another k tuple, then again repeat this process to another k tuple. Likewise we can continue indefinitely. So not only do we have only one k tuple, but infinitely many such k tuples. Okay. So there is a multiplicative version. So I am not going into the detail of this. So if you consider q square root d plus 1, d plus 2 up to d plus k, you can also consider q square root 2d, 3d up to k times d. The proof is almost similar. You just, in fact, in this case, the proof is in fact easier because the discriminant is appearing in a multiplicative way. So it is easier to catch hold of the prime divisors of the discriminants. So I am not going into this. So let us come back to this Polya groups. Now this theorem says that for any integer k bigger than or equal to 1 and m be a real number, then there exist infinitely many quadratic fields whose Polya group has order bigger than or equal to m. Earlier we had a result on class number. Now the question is, what about its subgroup? The technique is almost same. So we have to consider these quadratic fields and take care of the result of the size of the Polya group of a quadratic field. So remember in the beginning of the talk, I said that a quadratic field q square root d will have order 2 to the power number of ramified primes minus 2 if it is real quadratic field and its fundamental unit has norm 1, and otherwise if it is imaginary then it will have 2 to the power number of ramified primes minus 1. So we have to ensure that too many ramified primes are there, with the condition, if we want to have for the result for real quadratic field, that the norm of the fundamental unit is 1. So in the proof of this previous theorem, we just slightly tweak the technique for the prime numbers pij's. So not only do we choose the primes pij's, but also from the arithmetic progression congruent to 3 modulo 4. Why? Because when we have the quadratic field q square root d plus I, then d plus I will have pij as a factor. So if some integer d has a prime factor which is 3 mod 4, then its fundamental unit must have norm 1, because if the norm is minus 1, then we will have a Diophantine equation x square minus dy square equal to minus 1. Now we reduce this equation modulo the prime p, that gives us x square is congruent to minus 1 modulo p, where p is 3 mod 4. That means minus 1 is a quadratic residue mod p when p is 3 mod 4, which is clearly false. Therefore, if we are true, if we allow only one prime which is 3 mod 4. So if we do that, then the norm is 1 for the fundamental unit. Therefore, by the result of Hilbert, it says that the order of the Polya group is 2 to the power number of ramified primes, which is n. So it is again bigger than m, and we get a much bigger Polya group. Okay. Now comes the notion of consecutive biquadratic Polya field. So we define the notion of consecutive quadratic fields like q square root d and square root d plus 1. So the natural question is, what should be a good definition for consecutive biquadratic fields? So this is one definition that we had followed, that q square root m comma square root n, if we denote this field by k m comma n, then we call two such fields to be consecutive if they are of the form q k m comma n and k m comma n plus 1. So we are not touching the first coordinate, only the second coordinate we are making a little change. You can also define similar notion for m, keeping the second coordinate fixed and varying the first one. Yeah, or you can vary both. That will make a difference. So with this definition, in a recent work with Devopam Chakraborty and Imdadul Islam, we proved that if p and q are two odd primes and they are related by p equal to 2q plus 1, these are called Sophie-Germain primes, and we fix two such primes p and q, let's say 5 and 11 are such primes, then there exist infinitely many consecutive biquadratic fields of the form k m comma p minus 1 and k m comma p, such that both their Polya groups are isomorphic to some finitely many copies of Z mod 2Z. Okay, and the technique that we have followed here is essentially varying the first quadrant m. So if you want to keep m fixed and vary p, then we have to rely on a conjecture of the infinitude of Sophie-Germain primes. So if you want to have a result saying that there exist infinitely many such pairs where the first quadrant, the coordinate km is fixed and the second coordinate is varying, then we have to rely on the conjecture. But apart from that, this result is unconditional if we are allowed to vary only m. So let me give just a sketch of this proof. So for p and q are odd primes related by this equation, p equal to 2q plus 1. So clearly q is either 1 mod 4 or 3 mod 4. In both these cases, p is coming out to be 3 mod 4. Now for any arbitrary odd integer t, now we are taking odd because our target is to make the Polya group as large as possible. So the parity of t is in our hand. So we, for any odd integer t, we first choose prime numbers r1, r2, rt coming from this arithmetic progression 1 mod 8pq, and with the Legendre symbol condition ri by rj equal to minus 1. This can be done with the help of Dirichlet's theorem for primes in arithmetic progression and Chinese remainder theorem. Now for this choice of r1, r2, rt, let us denote the product of these integers by m, and then we call the biquadratic field k m comma p to be q square root m comma square root p. Now for this field, we apply this result of Xanten. Now, what this result says is that if you have a finite Galois extension, then you look at the ramification indices of the primes, rational primes that are ramified in K. Then we have an exact sequence from the first cohomology group to this direct sum of Z mod EIZ to the Polya group. So, the Polya group is the quotient of the middle term and the first term. So, if you want to have a bigger Polya group, then you have to throw many primes, rational primes that are in fact ramifying in K over Q, and together with that you need to control the cohomology group. So, for that we know that 2p, R1, R2, RT, these are precisely the primes that are ramifying in the biquadratic fields, because these are the prime factors appearing in the quadratic subfields. So, already we get t plus 2 many ramified primes there. So, now some cohomological result gives us that the order of the cohomology group is nothing but Z mod 2Z to the power 3. Now, t was in our hand. So, Z mod 2Z, t plus 2 many copies. Now, since t is in our hand, that is as large as possible, but the quotient is only 3 copies of Z mod 2Z. Therefore, when we take the quotient, the Polya group of K m comma p, that is t minus 1 many copies of Z mod 2Z. Therefore, t is arbitrary. Therefore, this is large. Okay. Similarly, if we articulate the same technique for K m comma p minus 1, we will again find that this is also isomorphic to t minus 1 copies of Z mod 2Z. Therefore, for K m comma p minus 1 and K m comma p, for both these fields, the Polya group is isomorphic to the. No, this proof is unconditional. So, I am saying that in this proof, the field is like K m comma p minus 1 and K m comma p. Now, p is fixed, we are varying m, that is how we catch hold of infinitely many such pairs. Now, suppose one wants to keep m fixed and then vary p. So, let us say K 10 comma p 10 comma p minus 1 10 comma some q q minus 1, then we have to rely on the Sophie-Germain primes, infinitude of the family of Sophie-Germain primes. No, in this proof there is no Sophie-Germain prime is used. But in the proof that I had not mentioned, K m comma 2q, their Sophie-Germain thing is not required. I mean q equal to 2q plus 1. So, in order to find the cohomology group, the 2 torsion of the cohomology group, that is generated by some class. For that, this requirement is there, that q minus 1 is equal to 2p. So, the class of q minus 1 is nothing but the class of 2p. So, that also adds nothing more to that. Okay, so in the remaining 2 minutes, let me just give you the notion of consecutiveness for a cubic Polya field. So, unlike this case, we have to rely on the defining polynomial of a cubic field. So, if we have a cyclic cubic field, we know that this has to come from some irreducible cubic polynomial with discriminant a perfect square. Now, this is a much studied family of called simplest cubic field given by Schank in sometime mid 80s, that it is the splitting field of x cube plus n plus 3 times x square plus nx minus 1 over q. So, we call two fields to be consecutive if they are given by the splitting field of fnx and f of n plus 1 comma x. But unfortunately, we could not find any consecutiveness result here, because the technique that we had followed, this essentially relies on the density of square free values in an arithmetic progression, and most of the time that density is much smaller than half. So, there is no way we can ensure that there is some overlap, so that some consecutive result turns out. So, this is our result. And yeah, that is it. I am not going to the proof, I am running out of time. Yeah. Thank you. Yeah, if the Polya group is trivial, then that's a Polya field. Yes. Right. No. So you want to know the proof of that statement? Yes. So there is something called characteristic ideals in that ring of integers, int of OK. So that characteristic ideal, if that is principal, then this is a Polya group. And that proof essentially comes from the definition of Polya group or Polya field in terms of regular basis. And this characteristic ideals being principal, that can be related to some ideal being principal, which is being taken care of from the property of class group. So that's how we relate it from this Polya means polynomial to ideal level.
So from that exact sequence,
No, no. This will not tell anything about the polynomial thing. Yeah, that's. But we do not have any result that says about the vanishing of this cohomology group. All we can say is that how to control the order of that group. Yes. Yes. Yes, we can expect, but we cannot. No, but we cannot then identify the cohomology group. That's a problem. Yes. In fact, the study of this cohomology group is only precise for biquadratic fields. We do not know of much result about how to control this cohomology group for other numbered fields. That's why most of the literature, the result concerns about biquadratic fields. Yes, actually there is a result that says that for Galois number fields with density 1, the Polya group is equal to class group. Yes. Yes. Because if you look at the definition, it says that the Polya group is the subgroup inside class group generated by the ideal classes of ideals of same norm. Now, if something is Galois, then only the ramified primes are making the problem. Now, there are only finitely many ramified primes, and all the rest of the unramified primes, they are not contributing much. So that's why.
yeah.
Yeah, thank you very much. Yeah, it was a wonderful conference. In particular, we would like to thank Professor Attikari and Dr. Nilanjan Bak for organizing this conference. So they had a lot of work with everything. Yeah, we saw a lot of interesting research problems and research which is currently going on. And also our students were able to get a flavor of currently going on research. So in particular, I would like to thank all students who came even this Saturday to our talks. And now I would like to ask our revered registrar, Swami Kalishananda, to say a few words, address our conference with a few words.
I'll take only a few minutes. Om Asato Ma Sadgamaya Tamaso Ma Jyotirgamaya Mrityurma Amritam Gamaya Om Shanti Shanti Shanti. Dear faculty members, our students, staff, distinguished guests who were present here, first of all, I offer my namaskaras to all of you. On behalf of RKM Veri, our university, I extend my heartfelt thanks to all the resource persons who contributed to the 6-day workshop on combinatorics and number theory. Nowadays, UGC, it encourages university to engage in lectures, seminars or workshop in the form of sharing ideas in 3 fields mainly. One is that teaching and learning, second one is research, and third one is skill development and extension. And especially 2 areas. One is skill development and translational research. I don't know that in what form it will appear to mathematics department. Maybe whatever you have discussed today, it must be having some application on computer science or data science, so that the benefit will go to the masses. That is very important. That means the theoretical part of your knowledge should be practically applied, so that people and our country will be getting the benefit. Second thing is that we have to develop skill to our students also. Simply not only knowledge, but skill is very important. And that is the vision of our National Educational Policy, NEP 2020. Second part of that focus of UGC is that IKS, India's knowledge system, and that is applicable for mathematics also, because in the field of mathematics, you'll be finding that our traditional knowledge system have lots of contribution in mathematics also, especially Vedic mathematics. So you must be aware of that one. And UGC's this vision is aligned with Swamiji's vision also. And as a university, you are translating Swamiji's vision, and Swamiji tells that remaining rooted in Indian culture, we should explore science and technology, maybe Eastern, Western, whatever may be. And that is our vision. And I hope that like this workshop, we'll be organizing future workshop also, seminars also. And in that we'll be discussing lots of new areas and involving lots of research scholars, and resource person will be also from diverse universities. That is very important. Once again, I extend my gratitude to all the resource person who just shared their insights, and I thank all the staff members, students who participated in this seminar or workshop, and made it a success. Thank you all. Namaste. Om Shanti Shanti Shanti.
Yeah, thank you for your illuminating words. Yeah, now I would like to ask our outside visitors and contributors to the stage. I made a little, I prepared a paper. So first of all, Professor Ravindranath Tangadurai from HRI, Prayagraj. And yeah. Next, Professor Jaitra Chattopadhyay Vishwabharati, who gave just a talk. And Professor Shubho Shakar, who will still give a talk. And finally, Ratnadeep Acharya, Professor Ratnadeep Acharya. Oh, actually, I don't know what is inside. Ah, okay. Yeah. I think everyone knows him. He is now at AKM Vidya Mandya. Okay. Thank you very much.
Then he got a job at BIT Mesra. Now, I mean, again, he got one more job. Then he shifted to NIT Jamshedpur. Please, Subbu.
Thank you, sir, for the introduction. It feels great that my PhD supervisor is introducing me. And I would like to thank Adhikari sir for giving me this opportunity to speak here. The title of my talk is on some graphs arising from number theory. So I have arranged this talk into two parts. In the first part, I will give some basic definition, basic properties. And in the second part of the talk, I will talk about some special graph for which some properties of that graph will come from number theory. Okay, so let us begin by this historical problem. This is known as Königsberg 7-bridge problem. So this says that there was a city called Königsberg in Russia. The map, I mean, some portion was like that. There were 7 bridges, and which connects these 2 river island and these 2 river banks. Now the problem, you have to start from any of the land areas. You need to cover all the edges, all the bridges exactly once, and you have to come back to the same area where you have started with. Okay. So this is the problem, that you start from some area, some river, some land area. You find a walk which crosses all the bridges exactly once, and you have to come back to the same land area where you have started with. Now, if you try to solve this one, I mean by hand, you will see that you are not getting any such walk which satisfies this property. That means if you find any walk, you will find that at least one bridge you have to cross twice. Okay. Now this problem actually very old. This is 1700 problem in the year 1700. So, and to solve this problem, Euler developed some theory, and that theory in the modern day language we call graph theory. So what Euler did, Euler transformed this problem into a graph theory. So Euler transformed this problem into a graph theory problem. So by a graph, I mean it is a pair of vertices and edges. So vertices means all those A, B, C, D, and edges means there is a connection between them. So what Euler did, he find the graph related to this problem. What he did, he converted the land areas as vertices, and if there is a bridge between those two land areas, he will draw an edge. So if you convert that problem, so this is becoming the graph of that problem. So now the problem is that can you find in that graph the same problem now transformed into, can you find this graph, in this graph can you find a vertex and you find a arc such that all the edges in that arc, all the edges comes exactly once, and you have to get back to the same vertex. Now Euler in 1736 he showed that there is no solution to that problem, and in fact he gave some property of that graph such that from that property we can say that which type of graph will satisfy that property. So I will come back to that problem later. So now let us formally define what a graph is. So I am trying to make it very accessible to the MSc students also. So a graph G consists of a vertex set and a edge set. So where vertex is a non-empty subset and edge set is nothing but an unordered pair of distinct vertices of G. Now we denote this UV rather than this UV. Okay, so for example, if we consider a vertex set to be V1, V2, V3, V4, V5, and suppose the edge set is that one, so the pictorial representation will be this. If there is an edge V1, V2, we will draw a line between V1 and V2, and like that. Now here are some definition that if UV is an edge, then we will say that U and V they are adjacent, and V is said to be a neighbor of U, and the set of all neighbors of U is denoted by N of U. Now for example here, if you consider the neighbor of V2, the neighbor of V2 will be V1, V3 and V4 because there is a direct edge. And the cardinality of the neighborhood is nothing but called the degree of U. So therefore how many vertices they are adjacent to that vertex, that calls the degree. Now if degree of U is equal to k for every vertex, we say that that graph is k regular. Now this is the famous handshaking lemma which says that if you take sum of all the degrees, it will be equal to twice times the number of edge. So if you just calculate here, so here the degree of V1 is equal to 2, degree of V2 is equal to 3, degree of V3 is equal to 2, so it adds up to 7, then degree of V4 is equal to 4, 11, and plus degree of 5 is equal to 1, so 12. Left hand side is 12, right hand side is also 12 because there are 6 edges. Now a graph is said to be complete if between any two pair of vertices there is an edge, that is any two vertices are adjacent, and we denote a complete graph of n vertex by k of n. So therefore in other words, a graph which has n vertex is complete if and only if the degree of each vertex is n minus 1, that means it is n minus 1 regular. And here are some example of complete graph with 1 vertex, 2 vertices, 3 vertices, 4 vertices and 5 vertices. Now similar to that definition, a graph is said to be bipartite if you can partition the set of vertices into two subsets V1 and V2, such that if there is an edge, the edge will be either one end will be in V1 and another end will be in V2. So that means there is in between any two vertices of V1 there is no edge, between any two vertices of V2 there is no edge. And it is said to be complete bipartite if between every vertex of V1 there is an edge between all the other vertices of V2. Now if cardinality of V1 is equal to m, cardinality of V2 is equal to n, we denote this by km comma n. Now here the first example, this is an example of bipartite graph, but this is not complete bipartite. And the second example, this is a complete bipartite graph. So second example is nothing but k 2 comma 3. Now similar in the definition of group, we see group isomorphism. Similar the definition graph isomorphism is also there. So essentially they are looking different, but they are actually the same graph. This is the idea. So you say two graphs G and H are isomorphic if there exists a bijection between the vertex set of G to vertex set of H, such that it preserves the edge structure. That means if UV they are adjacent in G, if and only if phi of U phi V that will be adjacent in H. And we say phi is an isomorphism between G and H. For example, here these three graphs they are isomorphic. We can directly find an isomorphism. Now if two graphs G and H are isomorphic, so since there is a bijection between the vertex set of G and vertex set of H, so their cardinality must be same because there is a bijection. Similarly, the edge structure is also preserved. So number of edge in G, number of edge in H, that must be same. And also if I take the degree sequence, that is if I take all the degrees of U of the vertices of G and all the degrees of u of the vertices of H, they must be same as a multiset. I mean the multiplicity will be also same. So if G and H they are isomorphic, then the two graphs will satisfy these three properties, but the converse is not true. Suppose you have two graphs which satisfies these three properties, we cannot say those two graphs are isomorphic. So here I have given one example. Here if you see, all the three conditions are satisfied, but we cannot find any isomorphism between these two graphs. Okay. So all those conditions, they are necessary condition but not sufficient condition. So like in the case of group, we say an isomorphism phi from G to G is said to be an automorphism, and the set of all automorphism of the graph, it will form a group, it will denote by odd G, and it is trivial to observe that if the graph has n vertices, so then odd G will be subgroup of Sn, and odd G is equal to Sn if and only if G is either Kn or the, by this I mean it is an isolated graph, that is either it will be Kn or it will be a graph with n vertices where there is no edge. Sorry. Now a graph is said to be vertex transitive if odd G acts transitively on the vertex set. That means for any two distinct vertices x and y of G, we can find some automorphism phi such that phi of x is equal to y. So it is clear from the definition that if a graph is vertex transitive, then it must be regular. So because it will, I mean it will map the same degree vertex to same degree vertex. So therefore if it is vertex transitive, then it must be regular, but of course here also the converse is not true. You can find some regular graph which is not vertex transitive. Similarly, we define a graph is said to be edge transitive if odd G acts transitively on the edge set. That means if I have two edges, say E and W, so then we can have some automorphism phi which takes E to W. Now here is an example of a graph which is edge transitive but not vertex transitive. If we take this complete bipartite graph K M comma N, so this is an edge transitive graph, but if I take M is not equal to N, this is not going to be a vertex transitive graph. Now I would like to give the definition of self-complementary graph, which says, so first I will define what is a complement of a graph, and then I will define what is self-complementary graph. So let G be any simple graph, then the complement of G, this is defined by G complement, and for this G complement we are taking the vertex set of G complement at the same as the vertex set of G, and we are defining the edges in G complement like that. If U and V they are adjacent in G complement, if and only if U and V are not adjacent in G. So just we are taking the complement of that graph in the case of set. If you look at this one, for example, if I take the first graph to be G, second graph is nothing but the complement of that graph G. Now from the picture, if you merge that graph here, that is if you take those two graphs together, the graph weight you will get, that is the complete graph on 5 vertices K5. So therefore the number of edge in the first graph plus the number of edge in the second graph, that must be same as the number of edge in the K5, which is 5 into 5 minus 1 by 2. So this is true for in general any graph, that if we have a graph of n vertices, then the number of edge in G plus number of edge in G complement is nothing but number of edge in the complete graph, which is n into n minus 1 by 2. Now a graph is said to be self-complementary if G and G complement, they are isomorphic. Okay, that means there is an isomorphism between G and G complement. Now it is trivial to observe that if G and G complement, they are isomorphic, that means number of edge in G and number of edge in J complement, they must be same. So therefore that equation becomes twice times of number of edge is equal to n into n minus 1 by 2. So therefore for a self-complementary graph, we get number of edge is equal to n into n minus 1 by 4. So therefore since number of edge is integer, either 4 will divide n or 4 will divide n minus 1, because n and n minus 1 they are co-prime. So therefore if we have a self-complementary graph with n vertices, either n is 0 mod 4 or n is 1 mod 4. But here also the converse is not true. We can have some example of graph such that this condition is satisfied, but though that graph is not self-complementary. And here I have defined, I mean this graph I have given example in such a way that this graph is a self-complementary graph. Okay, now I define something called clique number and independence number. So a graph H is said to be a subgraph if the vertex set of H is subset of vertex set of G, and vertex set of H set of H is subset of H set of G. And a clique and a clique is nothing but a complete subgraph of G, and size of the maximum clique is denoted by omega of G. So that means if suppose for some graph omega G is equal to 4, that means it has a k4 inside that graph but not any k5. That is the meaning of maximum clique. And we define the opposite notion of this, which is the independent set. So which says that a subset S of vertices is called independent if no two vertices are adjacent. And size of the maximum independent set is called independence number, and this is denoted by alpha of G. So for example, in this graph, if you take the vertices U, V and W, they forms a independent set, because between U, V and W there are no edge. So here also, I mean in this here, the independence number for this graph is equal to 3. And it is clear that if the independence number of G is same as the clique number of G complement, and also independence number of G complement is same as the clique number in G. Now again I will go to some historical problem which says 4-color theorem. Many of you may be aware of this problem. So this says, suppose we want to color the map of India, I mean any map, then what is the minimum number of colors do we need to color the map of India such that no two states which shares a common border gets the same color. So what is the minimum number of colors we need to color the map of India such that no two states which share a common border gets the same color? So this problem is very much applicable, because suppose I want to buy a map, I don't want in that map the color of West Bengal and Jharkhand, they are same, so that I cannot distinguish that which part is in West Bengal, which part it is in Jharkhand. So therefore I want a map where if two states share the common border, they must be of different colors. Now if you try out this problem to color this one, you will see the 4 colors are enough. You do not need 5 or more than 4 colors. Now if you change this map to some different map, you will get that either you need 1 color or 2 color or 3 color or 4 color. Okay, I mean you cannot find any map which require 5 or more colors. So this is the famous 4-color conjecture at the time, that is every map is 4 colorable. So we also, I mean this problem also solved by using graph theory. So what we do, we convert this problem into graph theory problem by taking the states as the vertices, and we define the edges. If they share a common border, then we define that they are adjacent. So in that graph theory language, now our problem becomes this, that what is the minimum number of color we require to color the vertices such that no two adjacent vertices gets the same color, because now our adjacent vertices is nothing but states which share a common border. So now this problem, so the history of the problem is that the first step is to show that if we convert a map to a graph like this way, then we will get a special type of graph, and that graph is known as planar graph. So if you convert any map to a graph like this way, then not an arbitrary will come as the graph of that map. It will be a special type of graph which is known as planar graph, and this is the definition of planar graph. A graph is said to be planar if there exists a drawing of G in the plane such that all the edges intersect only at the vertex point. Okay, for example, if you take A4, in the first representation, it is intersecting at a point which is not a vertex, the middle point. But if you consider this and this 2 representation, here no, all the edges, they are intersecting only at the vertices. So therefore this K4 is a planar graph, because we have at least one representation like that. But we can prove that K5 is not planar, and between, I mean Kn, where n is bigger than or equal to 5, that is not planar. And if you take the complete bipartite graph K3, 3, that is also not planar. So therefore all those type of graph K5 and K3, they will not come as a graph of some map. Now our problem becomes that what is the minimum number of colors do we require to color a planar graph such that no two adjacent vertices gets the same color, to solve this 4-color theorem, 4-color conjecture, I would rather say now. Now we can define some number, chromatic number. So this is the minimum number of colors K we require to color the vertices such that no two adjacent vertices gets the same color, and this number we denoted by chi of G. So therefore if number of vertex is equal to n, so therefore we have chi of G must be less than or equal to n, because we need at most n colors if the number of vertices is equal to n. And also we need at least one color, so therefore this is a trivial bound between chromatic number. Also we know that if chromatic number is equal to the upper bound, in that case it must be the complete graph. If it is lower bound, that is chi of G is equal to 1 if and only if the graph with no edge, that is there is no edge between that graph. And also we have this nice criteria that chromatic number is equal to 2 if and only if G is bipartite graph having at least 2 edge. Okay, this comes also trivially because suppose the graph is bipartite, so therefore there is the bipartition V1 and V2. So therefore between no vertices of V1 there is an edge, so we can color all the vertices in V1 by one color, and similarly we can color all the vertices of V2 by same color, because between no two vertices of V2 there is an edge. So therefore two colors are enough, and we can also find the converse part also. So this is an if and only if criteria. And also we have some upper bound and lower bound using the clique number and the independence number, which I have defined earlier. And also we have this upper bound chi of G is equal to capital del G plus 1, where delta is the maximum of degree, all the vertices. Now all those upper bound, all those bound, they are not very, I mean, good bound. They are some trivial bound, but till now I think there is no such good bound is there for chromatic number. Now this is the famous 4-color theorem, which is proved by Appel and Hanken, that if G is a planar graph, then chi of G must be less than or equal to 4. That means every map is 4-colorable. Now what their idea, how they proved this one, they proved that if we are taking a map, then we are finding a graph. So they proved that there are 1986 many graphs, such that if I convert a map to a graph, it will be one of those lists, 1986. And I precisely remember that number because if you add 10 to that number, you will get that number. So that is how I am remembering that. So in that list, and then they prove that all those maps in that list, they are 4-colorable using some computer search. So at that time, this proof was controversial because no one believed that a computer proof is there. I mean, no one believed that such a proof is acceptable in math. But now it is widely, I mean, it is acceptable, and till now this is the only proof we have, this computer search method. Of course, that list has been reduced from 1986, maybe it is now reduced to 800 or something. Okay, now here I define the path and connectedness. So now a walk in a graph, this is an alternating sequence of vertices and edges, such that EI is nothing but the edge Vi minus 1 Vi, and we say V0 is the origin, Vp is the terminus. We say this is an V0 Vp walk. It is said to be closed if V0 is equal to Vp, and walk is said to be a trail if all the edges appearing in this walk are distinct. It is said to be a path if all the vertices are distinct. It is called a cycle if it is a path where the beginning point and end point are same. And we say that two vertices U and V, they are connected if between U and V there is a path. That is, you can go from U to V via some path. And a graph is said to be a connected graph if any two vertices U and V there is a path. Okay. Now here I have given some example which is a walk but which is not a trail, because here this edge E7 is repeating. Next one is a closed walk. Next one is a trail but which is not a path because the vertex V1 is repeating. Last one, second last one is a path, and the last one is a cycle. And a cycle of length k is denoted by Ck, and a path of length k is denoted by Pk. Now I come back to the Konigsberg 7-bridge problem again. So this is the definition of an Euler trail. So an Euler trail in a graph G is a trail that contains all the edges. Now by a definition of a trail, all the edges are distinct. So therefore a Euler trail is nothing but a walk which contains all the edges exactly once. An Euler tour is a closed Euler trail. That is, we are taking the initial vertex and ending vertex are same. And our graph G is said to be Eulerian if it has an Euler tour. So if you remember the Konigsberg 7-bridge problem, it says precisely that graph is Eulerian or not. That is, can we find some closed Euler tour in that graph. Now here is the famous theorem that a graph G is said to be Eulerian, G is Eulerian if and only if the degree of each vertex is even. So if you go back to that graph from the Konigsberg 7-bridge problem, there we see that there is one vertex of degree 5. So therefore that graph cannot be Eulerian. So in that Königsberg 7-bridge problem, there is no such solution will be there. Okay, and this is the full classification of which graph is an Eulerian graph. Now, similarly, we define something called Hamiltonian graph. So, a Hamiltonian cycle in a graph, this is a cycle which contains all the vertices exactly once. So, earlier we said that it is Eulerian if it contains all the edges exactly once. Here we are saying if it contains all the vertices exactly once. And our graph is said to be Hamiltonian if it has a Hamiltonian cycle. Now, there is a sufficient condition for Hamiltonianity that if G is a simple graph with degree of each vertex is bigger than or equal to n by 2, so then G is Hamiltonian, but this is only a sufficient condition, this is not necessary one. Now, I define something called adjacency matrix. So, this is the bridge between linear algebra and graph theory. So, suppose we have a graph G with n vertices, suppose we label the vertices as v1, v2 dot up to vn. We define the adjacency matrix of G like this. So, it is an n cross n matrix. The ijth entry is equal to 1 if vi is adjacent to vj, and ijth entry is equal to 0 otherwise. Okay. Now, it is clear from the definition that if you take the row sum or column sum, that is nothing but the degree of that vertex. If we take the row sum of the matrix, so this matrix is a 0, 1 matrix. It is 0 if vi and vj are adjacent. It is 1 if vi and vj are adjacent. It is 0 if they are not adjacent. So, if you take the row sum, it will be the degree of that vertex u. And of course, because we are not considering any self loop, that is vi is not adjacent to vi, all the diagonal entries must be equal to 0. And if vi and vj they are adjacent, so then vj and vi they are also adjacent. So, it is a symmetric matrix. ijth entry will be same as jith entry. So, these are the observations. Since it is a symmetric matrix with diagonal, since it is a symmetric matrix, so therefore all the eigenvalues must be real, and all the eigenvalues we will denote by that set to be the spectrum of that matrix A. Now, the spectrum of this matrix A we sometimes call this is the spectrum of the graph G also. Okay. Now, there are many relation between the invariant of the graph and the characteristic equation of this matrix. So, that many invariant relation are there. So, that is why to compute this eigenvalue is a very good, I mean, is a problem in this graph theory. So, here comes a definition. So, a matrix, this is a special type of matrix. A matrix of order n is called a circulant matrix if all the rows of the matrix we are getting by cyclic shift of a fixed row. For example, if I take the first row a1, a2, a3, so I am making a cyclic shift of the second row, that is a3, a1, a2 of the first row, and then the third row is a2, a3 and a1. So, all the rows are cyclic shift of the first row. So, this type of matrix is called a circulant matrix. And we have this result that if A is a circulant matrix, then we know how to compute the characteristic polynomial and how to compute the spectrum, that is how to compute the eigenvalue. And this is precisely the theorem says that where omega is the nth root of unity. So, this set forms all the spectrum of A. Now, here I have replaced this omega by this particular primitive nth root e to the power 2 pi I by n, so that we get this result. Now, if you consider the complete graph, if I take the adjacency matrix of complete graph, so this is the adjacency matrix of a complete graph, because at the diagonal it will be 0 and every other point it will be 1, because a complete graph is adjacent to all the other vertices. I mean, every vertex is connected to every other vertices. So, this is a circulant matrix with respect to the first row. So, therefore, if we apply that theorem, we are getting the spectrum of A is equal to that one. So, if I put omega to be equal to 1, we are getting n minus 1. If I put omega to be any other nth root of unity, we are getting minus 1. So, therefore, the algebraic multiplicity of n minus 1 is equal to 1, algebraic multiplicity of minus 1 is n minus 1. Okay. Now, I will come something that special graph. I am going perfectly with the time. So, I will define some graph which is known as Cayley graph. So, this graph comes from group. Okay. So, let us take gamma to be any finite group with identity E, and we are taking S as any subset of gamma with respect with these two conditions, that identity should not be inside S, and if A belongs to S, then the inverse of A is also belongs to S. That is, it is a inversely closed. Okay, this is closed under inversion, and we define a graph out of this like this. This is called the Cayley graph of gamma for that group S, for that subset S. So for that, the vertex set is all the elements of gamma. Vertex set is all the elements of gamma, and we define the edge set between A and B. There is an edge if A be inverse inside that set S. Okay. The vertex set is all the group element. Edge set is between A and B. There is an edge if A B inverse belongs to S. Now, since identity is not here, so that graph has no self loop. Since identity is not here, so the graph has no loop. And the inversion we are taking, this is closed pattern inversion, because we want if between A and B there is an edge, between B and A also there should be an edge. So that is why we want if A belongs to S, then A inverse also belongs to S. Now it is known that this graph is a regular graph of degree of each vertex is cardinality of that subset S. And also it is known that if that subset S generates that graph gamma, so then our Cayley graph is connected. Okay, if S generates gamma, so then the Cayley graph is connected graph. Now here I give the definition of a particular Cayley graph which is known as unitary Cayley graph. So for that we taking our set, we taking our group gamma is Zn with plus, we are taking S to be the group of all units. Okay, so this S satisfies all the condition because 0 is not a unit, and if A is a unit, then minus A is also a unit. So therefore this S satisfies all the condition. So therefore if we define the Cayley graph, corresponding Cayley graph, this is known as the unitary Cayley graph. So the vertex set is all the elements of Zn, so 0 1 dot dot up to n minus 1, and edge set is between A and B there is an edge if A B inverse is an unit, but here B inverse is minus B because we are taking with respect to addition. So if A minus B is a unit, now if A minus B is a unit, that means A minus B is co-prime to n. So therefore the GCD of A minus B comma n is equal to 1, and it is since 1 belongs to S, so therefore S generates gamma. So therefore our graph is connected. It is a regular graph with common degree, number of element of S, which is nothing but phi n, which is the Euler-Tauschent function, because that is the cardinality of U1. Now if n is equal to prime, then the common degree is nothing but phi p, which is p minus 1. So therefore we are getting that is a complete graph. So if n is equal to prime, then xp, that unitary Cayley graph, this is p minus 1 regular. So therefore that is a complete graph. Now here so we have a theorem for the precise chromatic number of that unitary Cayley graph, which says the chromatic number of Cayley graph xn is equal to p, where p is the smallest prime divisor which divides n. If p is the smallest prime divisor of n, then the chromatic number of xn, which is same as the clique number, which is equal to p, and the chromatic number of xn complement, the complement graph, is same as the clique number of complement graph of xn, which is equal to n by p. Now here I try to give a proof of this result. So if I consider this 0 1 dot dot up to p minus 1, then they forms a clique between, if I take, because if I take any two elements between 0 and p minus 1, their difference is less than p. So it is co-prime to p, and since p is the smallest prime, it is co-prime to all the other prime divisor also. So therefore this forms a clique, and here the clique, this size of this clique is equal to p, and omega is the size of the maximum clique. So omega of xn must be bigger than or equal to p, because omega is the size of the maximum clique, and here we got one clique. And by that bound of chromatic number, we have chromatic number of xn is bigger than or equal to the clique size, which is bigger than or equal to p. Now to prove the other direction, we see that if I take all the residue classes modulo p inside Zn, so if I take any residue class, that will form an independent set, because if I take any residue class, the difference between any two element is divisible by p. So therefore it cannot be a unit. So therefore all those elements, they must be independent. There is no edge between any two element. So therefore all that independent set we can color by using single color. Since there are total p many residue classes, we can color all of them by p colors. So therefore chromatic number must be less than or equal to p. So this shows the inequality, chromatic number of xn is equal to p, and I am not going to prove the other one. So this gives some important corollary which says, so therefore if our n is even, then the chromatic number is equal to 2. If n is even, then the chromatic number is equal to 2, because p is equal to 2 there. And we have seen that chromatic number is equal to 2 if and only if our graph is bipartite. So therefore, the unitary calligraph is bipartite if and only if n is even. Okay. Also, we get some corollary using the self-complementariness, that no xn is self-complementary. This is the next result, next corollary, that no xn is self-complementary. Suppose some xn is self-complementary, so the chromatic number of xn and chromatic number of xn complement, they must be same, because the graph are self-complementary. So therefore, in that case, p must be equal to n by p, so n must be equal to p square. And also we have seen that if you have some self-complementary graph, in that case twice time number of edge is equal to n into n minus 1 by 2, and from the handshaking lemma we get that the left hand side is nothing but n times phi of n. So from there we will get phi of n is equal to n minus 1 by 2, and this is a contradiction because our n is equal to p square, then phi of n cannot be n minus 1 by 2. So this gives a contradiction, so therefore there is no xn which is self-complementary. And also we have some Hamiltonian and Eulerian property of that graph. So xn is Eulerian because we have seen the degree of every vertex is equal to phi n, which is even if we take n bigger than or equal to 3. So therefore every xn is Eulerian, and it is also Hamiltonian because we have this Hamiltonian cycle starting from 0 ending at 0. Now we take this particular automorphism. If I take A to be any unit and B to be any element in Zn, so if I define psi of AB like that, so we can easily show that this is an automorphism of the graph, and this psi of AB that forms a subgroup which acts transitively on the vertices and the edges of the unitary calligraph. So therefore we have this result that xn is both vertex transitive as well as edge transitive, because this is a subgroup which acts transitively. Now here I would like to compute, this number we would like to compute the number of triangles in that unitary calligraph xn. That is how many k3 are there in that graph. So for that we need this result which has a flavor from number theory. So it says that if we take fn of s to be the number of solution of this congruence, x plus y equal to s modulo n, where x and y varies over unit, then the number of solution to this congruence is given by this formula. So where epsilon p is either equal to 1 or either equal to 1 or 2 if p divides s and if p does not divide s. Now the proof is not very difficult. First we need to prove this from prime power. We will find some value, that value is easy to compute. Then using Chinese remainder theorem we can lift that result to general n, and then that number will be product of all such numbers. So this is how the proof comes. Using this result we will try to show that if we have any two distinct vertices a and b of xn, the unitary calligraph, so then the number of common neighbors is given by fn of a minus b, where fn of s is nothing but solution of that congruence problem. So by a common neighbor I mean z is a common neighbor of a and b, that means between z and a there is an edge and between z and b there is an edge. So suppose z is a common neighbor, so therefore between z and a there is an edge, so a minus z will be co-prime with n. Similarly between z and b there is an edge, so GCD of z minus b comma n, that is also equal to 1. So we will take x and y to be a minus z and z minus b. Now if we see, we will get that z equal to a minus x, which is equal to b plus y. So therefore z is a common neighbor if and only if x plus y is congruent to a minus b modulo n, where x and y varies over the unit, and this is nothing but fn of a minus b. So this means the number of common neighbor is equal to fn of a minus b. Now in addition to that, if we want that our a and b they are adjacent, so then the number of common neighbor will be equal to this number. So if I more in that lemma, if I require that between the vertices a and b are adjacent, and then I want to count what is the total number of neighbors of a and b, in that case we will get this number. So this is coming because suppose z is a common neighbor, so number of common neighbor is fn of a minus b. Now since a and b they are also adjacent, so a minus b is a unit. Now if a minus b is a unit, that means p does not divide a minus b. So in that case we will get in the value of epsilon p to be equal to 2. So that is n into product of 1 minus 2 by p. So we will get that result, product of n into 1 minus 2 by p. So from using this result we can count how many triangles are there. So total number of triangles is given by this formula. Now it is also known that if I denote pkn to be the number of k cycle, then the number of force cycle is given by this formula. And we know what is the length of the longest cycle, which is given by 2 to the power r plus 2, where r is the number of distinct prime divisors. Now we know this result, these are some result we know. I will not going to say all those things. Now let us come to the adjacency spectrum of this unitary calligraph. So if I take the adjacency matrix of xn, it will come as a circular matrix. That means every row is coming as a cyclic shift of the first row. So therefore, if this is the result we have already seen, then the spectrum of the circular matrix is given by this formula. Now the first row is nothing but adjacency corresponding to the vertex 0. Now 0 is adjacent to I if and only if GCD of I comma n is equal to 1. So therefore, corresponding AI will be equal to 0 if GCD of I comma n is bigger than 1, and it will be equal to 1 GCD of I comma n is exactly equal to 1. So therefore, we will get a spectrum of AN like this, and this is the well-known Ramanujan sum in the number theory, and some properties, I mean we know that the Ramanujan sum is given by this result, and we know that all the Ramanujan sum they are integer. So therefore, we have all the eigenvalues of unitary calligraph, they are all integer and they are given by the Ramanujan sum. We can, in fact, we can say more of the thing, that if m is the maximal square free divisor of n, then the minimum spectrum is given by this formula, and every other eigenvalue is a multiple of this one. And if lambda n is odd, then lambda min is the only non-zero eigenvalue of minimal absolute value, and if n is even, then lambda minus of lambda min is also an eigenvalue, and also the multiplicity of 0 as an eigenvalue is n minus m. So from here we are getting this corollary, that if either plus or minus 1 is an eigenvalue, in that case we will get n must be a square free number, and if both of the plus and minus 1 comes as an eigenvalue, then we are getting n must be if and only if square free and even. So these are all corollary of this result. Now here I would like to give some generalization of unitary calligraph. I have 2-3 minutes left. So we generalize this one, like suppose D is a subset of all positive proper divisors of n. Now we define the GCD graph. So all the vertex are same, the Zn 0 1 dot dot up to n minus 1. We are taking the edge set between A and B, there is an edge if GCD of A minus B comma n now belongs to D, some set of all positive, some subset of positive divisor of n. So if our D is equal to 1, this is nothing but unitary calligraph, and so this is a generalization. There are and we know that this is connected if and only if the GCD of all the elements of D must be equal to 1. And also the eigenvalues of GCD graph, they are given by this integer. This is also sum of this Ramanujan sum, so they are also integer value. Now another generalization is there of unitary calligraph, which says that now we define the edge set like this: between A and B there is an edge. Earlier it was A minus B is in unit, here we are taking A plus B is a unit. So that is why this is called unitary addition calligraph or unit graph. In fact, there are some more generalization which says that now we are taking the edge set like between A and B there is an edge if A plus UB is a unit for some unit U. Now there are not that much result for this, the last generalization. I have seen only few results of that. So I mean, if someone can one can explore that one, but there are some results of unitary addition calligraph. And next I would like to give another generalization, which is a palette type graph. So if I take n to be this form 2 to the power s pi alpha I, where s is equal to either 0 and 1, and all the pi's are of the form 1 mod 4. So then here they have defined the edge set like this: between A and B there is an edge if A minus B not a unit but it is an unit square, that is it is a quadratic residue. So why we want this pi congruent to 1 mod 4 condition? So because if between A and B there is an edge, we want between B and A also there is an edge. So that means we want both A minus B and B minus A are quadratic residue. So therefore minus 1 must be a square, and to have minus 1 is a square, we want all this condition pi congruent to 1 mod 4. Now in that paper they have also proved that if n is odd, then they obtained the number of cliques of order 3 and order 4, that is how many k3 and k4 are there inside that graph. And the case n equal to pq, where p and q are 1 mod 4, that has already studied some other paper. And actually this is the graph I have given one of my MSc project student this time, and we have got some result, but that was not, I don't feel that is publishable here. I mean, that were some trivial observations. So one can see this generalization, because as far as I know, in this generation, in the first generation, only the number of clicks of order 3 and order 4 have been discussed. So I mean, if one can explore this generalization, because there are lots of questions will be there which can be worth to pursue. And for this second case, n equal to pq, there are many results of unitary calligraph type there, that what is the chromatic number, what is the diameter, whether it is Hamiltonian or not, whether it is Eulerian or not. So all of the things you can see in that generalized version. I hope there are no results there. So I would like to end here. These are the references. So I have taken the graph theory definition from the first book, and that unitary calligraph from the last number 8, that was there. And for palette graph I have taken 3 and 4. Okay, these are the references. Thank you very much for your attention.
So you told that there is a computer, there is
Huh.
proof not for that portal.
Yeah.
So is any result known for easy proof known for the chromatic number is 5? Means it is
Yes. Yeah, there is some proof. Yeah, there are some proof for 5, for 6 also. Yeah, for 5 and 6 there are proof. So that uses that result, that if we have a planar graph, then there is a vertex whose degree is less than or equal to 5. So that is explored. But for 4 we have, I think we have only this computer programming proof. Yeah. Yes. Honestly, I don't know. Okay, thank you. Okay.
so I should thankful to the organizers for the workshop.
No, পাঠাতে হবে না।
Several type of talks which was interesting.